Welcome back. In this video, we're going to be looking at example problems of calculating the arc length of curves by using definite integrals. Let's get to it. All right, so here's our first example. We want to find the arc length of the curve f of x equals x minus 1 to the 3/2 power for the values of x between 1 and 5. All right, and so in order to calculate the arc length, we need to know the formula for calculating the arc length using definite integrals. And so since our function is given to us in terms of x, we are going to be working in terms of x. And so our arc length formula will look like this. The length is equal to the integral from a to b, which are two values of x, of the square root of 1 plus f prime of x, the derivative of our function, squared times dx. Okay, and so in order to set up this definite integral, we need to find the derivative f prime of x of our function. And so f prime of x will be equal to the derivative of x minus 1 quantity to the 3/2 power. And so in order to take the derivative of this function, note that we have a composite function, which means that we need to use the chain rule. We'll start by taking the derivative of the outside function and then multiply by the derivative of the inside function. And so we'll use the power rule for our outside function. We'll multiply 3/2 down and then subtract 1 from the exponent. That's what the power rule tells us to do. So we'll have 3/2 times x minus 1 to the power of 1/2. Right? 3/2 minus 1 is equal to 1/2. And then we need to multiply by the derivative of the inside function x minus 1. But the derivative of x is just 1, since the derivative of x to the first power is just equal to its coefficient, which is 1 in this case. And the derivative of -1 is 0, since -1 is a constant. And so we're just multiplying by 1. That is the derivative of our inside function. And so if we rewrite our derivative here, note that the 1/2 power is the same as the square root. And so this is equal to 3/2 times the square root of x minus 1. Okay, and so now we can plug this derivative into our arc length formula, and we can solve for the arc length in this problem. So we will have that the arc length is equal to the definite integral from a to b. Now in this case, that's going to be two values of x for which we want to calculate the arc length between for our function. And we're told that we want to look at the x values between 1 and 5, right? 1 is less than or equal to x, which is less than or equal to 5. So our bounds of integration will be from 1 to 5. And then we'll have the square root of 1 plus our derivative squared, which is 3/2 times the square root of x minus 1, and then we'll square that. And then don't forget to multiply by dx. All right, so we wrote in our bounds of integration and plugged in our derivative for f prime of x, and now we are ready to solve this definite integral to find the arc length of our curve. And so this will be equal to the integral from 1 to 5 of the square root of 1 plus 3/2 times the square root of x minus 1 squared. Now we can square each of these factors, so 3/2 squared will be 3 squared divided by 2 squared, and so that will be 9/4. And then if we square the square root of x minus 1, the square and the square root cancel out, and so we'll just be left with what is inside the square root function. And so we'll just be multiplying 9/4 by x minus 1, and then we still have dx. Okay, and so to simplify further, we can distribute this 9/4 through this quantity, and so we'll have that this is equal to the integral from 1 to 5 of the square root of 1 plus 9/4 times x minus 9/4. And then we still have dx. Okay, and then we can combine our like terms. We have 1 and -9/4 that we can combine. And so if you subtract 9/4 from 1, you'll be left with -5/4. And so this will be equal to the integral from 1 to 5 of the square root of 9/4 times x minus 5/4 times dx. Okay, and so if we clean up our work here, we now have a definite integral that we can solve to find our arc length. Now in this case, we have a composite function in the integrand, and so we're going to need to use u substitution, but you want to make sure that whatever you set equal to u, you can find its derivative in your integral. In this case, we want to set u equal to that inside function, so we'll have the square root of u. And the derivative of x to the first power is just equal to a constant, and so we'll be fine. We can use u substitution here without any extra manipulation like you might have to do in some other arc length problems. And we'll look at that in our other examples, but for now, we can just set u equal to this inside function, and we can start solving this integral. So u will be equal to 9/4 times x minus 5 divided by 4, And the derivative, du dx, will be equal to 9/4 because the derivative of x to the first power is just equal to its coefficient, 9/4, and the derivative of -5/4, which is a constant, is just 0. All right, and so if we multiply both sides by dx, then du is equal to 9/4 times dx. And now whatever du is equal to, you need to be able to find that within your integral. However, I don't see a 9/4 that we can replace with du, and so I'm going to divide both sides by 9/4, which is the same as multiplying by 4/9. And so we'll have that 4/9 times du is equal to dx. And now we have a term of du that can replace something we can find in our integral. And so, if we replace this inside function with u and replace dx with 4 divided by 9 du, then our integral will be rewritten in terms of u. And so we'll have that this is equal to the integral from 1 to 5 of the square root of u times 4/9 times du. And so now if we pull this 4/9 to the front of the integral, this will be equal to 4/9 times the integral from 1 to 5 of the square root of u times du. And so now we have our integral in terms of u, and so now we can integrate. And note that the square root of u can be rewritten to be u to the 1/2 power. So let me do that real quick. We'll have u to the 1/2 power, and now we can more easily see how to use the power rule of integration. We'll add 1 to that exponent, and then divide by that new exponent. And so this will be equal to 4/9 times u to the 3/2 power divided by 3/2 evaluated from 1 to 5. Right, 1/2 plus 1 is 3/2, so that's our new exponent, and then we divide by 3/2. And so now if I clean up my work, we can simplify this a little bit, and so note that dividing by a fraction is the same as multiplying by that fraction's reciprocal, and the reciprocal of 3/2, if we switch the numerator and the denominator, is 2/3, and so we'll have that this is equal to 4/9 times 2/3 times u to the 3/2 power evaluated from 1 to 5. Now we can pull that 2/3 outside and multiply it by 4/9, and then we can replace u with what we set it equal to so that we can then evaluate that expression at 5 and then subtract the evaluation at 1. And so remember, u is equal to 9/4 times x minus 5/2, and so what we'll have is that this is equal to 4/9 times 2/3 times u, which is 9/4 times x minus 5/4 to the power of 3/2 evaluated from 1 to 5. Okay, so we just replaced u with what we set it equal to, but that still needs to be taken to the 3/2 power since u was also to the 3/2 power. Now 4 times 2 is 8 and 9 times 3 is 27, so this will be equal to 8/27. And so if we clean up our work, we'll have that this is equal to 8/27 times the evaluation of this expression at 5 minus the evaluation of this expression at 1. So we will have 9/4 times 5 minus 5/4 to the power of 3/2 minus 9/4 times 1 minus 5/4 to the power of 3/2. All right, and so if we simplify, this will be equal to 8/27 times 9/4 times 5. That will be equal to 45/4 minus 5/4. But note that 45/4 minus 5/4 will just be equal to 40/4. And so I'll rewrite that. We will have 40/4, and that will still be taken to the 3/2 power, minus 9/4 times 1. That's what we have right here. That's just equal to 9/4. So we have 9/4 minus 5/4. And 9/4 minus 5/4 is 4/4, which is just equal to 1. So we'll rewrite that to be 1, and that will still be to the 3/2 power. Now we can simplify one more thing here, and that is 40 divided by 4 is the same as 10. I should have done that earlier, but let's rewrite that now. That's equal to 10. And so this will be equal to 8/27 times 10 to the 3/2 power minus 1 to the 3/2 power, but 1 to the power of anything is just 1, so we will have 1. Okay, and so this will be our final answer. We cannot simplify this any further, but this isn't a very satisfying answer. It looks pretty ugly. And so while this is the correct answer, we could also plug it into our calculator to get an approximate value. And if you did that, it would be approximately equal to 9.07 and then some more decimals. But that is the approximate value of the arc length of this function from x equals 1 to x equals 5. So here's our next example. We want to find the arc length of the curve f of y is equal to 1/3 times the quantity y squared plus 2 to the 3/2 power from y equals 0 to y equals 1. All right, so in this case, we're working in terms of y. So our arc length formula will look like this. We'll have that the arc length is equal to the integral from c to d, which are two values of y, of the square root of 1 plus the derivative f prime of y squared times dy. Okay, so since our function is in terms of y, our derivative will also be in terms of y. And so let's find that derivative. Let's find f prime of y so that we can plug it into this formula. So f prime of y will be equal to the derivative of this function right here. Now once again, we're going to need to use the chain rule since we have a composite function. And so I'll start by taking the derivative of the outside function and then take the derivative of the inside function. Okay, so we'll start by using the power rule. We'll multiply 3/2 down and then subtract 1 from that exponent. So we'll have 1/3 times 3/2, and that will be multiplied by y squared plus 2 to the 1/2 power, right? If we subtract 1 from the power of 3/2, we will be left with 1/2, since 3/2 minus 1 is 1/2. And then we need to multiply by the derivative of the inside function, which is y squared plus 2, and the derivative of y squared, if we use the power rule, we'll multiply the 2 down and subtract 1 from that exponent, so we'll have 2y, and so we'll be multiplying by 2y, and that's it because the derivative of 2 is just 0, since 2 is a constant. Okay, and so if we simplify, note that this 3 and this 3 will cancel out, and so this will be equal to 1/2 times y squared plus 2 to the 1/2 power times 2y. But then this 2 and this 1/2 will cancel out to just be 1. And so what we have is that this is equal to y times this quantity to the 1/2 power, which is the same as the square root. So we'll have the square root of y squared plus 2. Okay, so that's our derivative, f prime of y. And so we can plug that in to our arc length formula. And then the only other thing we need to know are our bounds of integration, or what two values of y we are interested in finding the arc length between, which in this case is y equals 0 and y equals 1. And so we'll have that this is equal to the integral from 0 to 1 of the square root of 1 plus our derivative y times the square root of y squared plus 2 squared times dy. Okay, and so if we simplify, this will be equal to the integral from 0 to 1 of the square root of 1 plus the derivative squared. Now we can square each of these factors since they're multiplied together. So we'll have y squared and then this square root function squared. Now y squared is just y squared. So we'll have y squared times this square root squared, and those will cancel each other out. So we're just going to be left with what is inside the square root, which is y squared plus 2. And that's still multiplied by dy. And now if we simplify further by distributing this y squared through this quantity, we will have that this is equal to the integral from 0 to 1 of the square root of 1 plus y to the 4th power plus 2 times y squared times dy. All right, and so now if we clean up our work, we now have a definite integral that we can solve to find the arc length of our curve from y equals 0 to y equals 1. However, it's not initially obvious how we are going to solve this definite integral, right? We know we have a composite function, and so we're probably going to want to use u substitution, but if we set u equal to this inside function, note that the derivative of that function is not also found within our integral, right? You need to be able to find a derivative of whatever you set equal to u in your integral in order to use u substitution. And so what we need to do here, because currently we can't use u substitution, is try to manipulate what we have here so that we can recognize how to integrate this function. And so what I'm going to do is reorder these terms a little bit, and then I want you to notice something about what we have. So this is going to be equal to the integral from 0 to 1 of the square root of y to the 4th power plus 2y squared plus 1 times dy. All I did was move this 1 to the end of our terms, right? This is equivalent to what we have up here because it doesn't matter what order you add things in. But now what we have here is a polynomial that we can factor, right? So this polynomial is in the form of a squared plus 2 times a times b plus b squared. And this can be factored to be equal to a plus b times a plus b and that is equal to a plus b squared. And here's how I know that it's in this form. If we let y to the fourth power be equal to a squared, right, so we'll have a squared is equal to y to the fourth power, and we take the square root of both sides, that means that a is equal to y squared, and we let b squared be equal to 1, so we'll have b squared is equal to 1, and then if we take the square root of both sides, we have that b is equal to 1. And so now, notice that if we let a equal y squared and b equal 1, that this is in the form of this right here. A squared is y squared squared, which is y to the fourth power, which is what we have right here. 2 times a times b will be 2 times y squared times 1. And that's what we have right here for our middle term. And then b squared is, of course, 1, which is what we have right here. All right, so you want to try to work on being able to identify polynomials that can easily be factored, like this one. Okay, so another form that you might want to be aware of is that if this middle term is negative, so if that was negative 2ab, then your factorization would be slightly different. You would have a minus b times itself, and so that would look like this. You'd have a minus b times a minus b, and then that would be a minus b squared. All right, so that's another form that you might want to be aware of, but being able to recognize that will allow you to simplify your integral in this case. So what we'll have is that this is equal to the integral from 0 to 1 of the square root of this polynomial factored. Now remember, we said a was y squared, so we'll have y squared plus b, which was 1, and so we'll have 1 squared times dy. Okay, so that's how we factor this polynomial, and now notice we have a square root of a quantity squared, and so those will cancel out, and so we'll have that this is equal to the integral from 0 to 1 of just y squared plus 1 times dy. And so now if I clean up my work, we can solve this integral, which is a pretty simple one now, and so we'll have that this is equal to the integral of y squared, which is going to be y cubed divided by 3, plus the integral of 1, which is just y, and that will be evaluated from 0 to 1. Right, we use the power rule of integration on y squared by adding 1 to the exponent and then dividing by that new exponent. And then the integral of 1, which is a constant, is just equal to that constant times the variable of integration, which in this case is y, which we know by looking at this dy here. dy tells us that we're integrating with respect to y. Okay, and so now we can evaluate this expression at 1 and subtract the evaluation at 0. So this will be equal to 1 cubed divided by 3 plus 1 minus 0 plugged into y cubed divided by 3. That's just 0, and then plus 0 is still 0, so we're just going to be subtracting 0. And so this is equal to 1/3 plus 1, which is equal to 4/3. And 4/3 is the arc length of our function from y equals 0 to y equals 1. All right, let's look at one more example for this video. Okay, so here's our last example. We want to find the arc length of the curve y equals 1/3 times the square root of x times the quantity x minus 3 from the point 0, 0 to the point 4 2/3. Okay, and so since we're given a function in terms of x, we know that we are going to be working in terms of x, and so our arc length formula will look like this. The length is equal to the integral from a to b, which are two values of x, times the square root of 1 plus the derivative f prime of x squared times dx. Now in this case we have y equals our function, and so you could rewrite f prime of x to be y prime or dy dx. It doesn't matter, just know that this represents the derivative of whatever curve you are working with. And so let's find that derivative, but first I'm going to simplify our function a little bit. So we have y is equal to 1/3 times the square root of x times x minus 3. We can rewrite the square root of x to be x to the 1/2 power, and if we do that, we can then distribute x to the 1/2 power through this quantity, and then we'll more easily be able to take the derivative. That way we don't have to use the product rule like we would in its current state. And so if we do that and distribute this 1/3 as well through this quantity, we will have that this is equal to 1/3 times x to the 3/2 power minus x to the 1/2 power. Right, so when you multiply x to the 1/2 power times x to the first power, we add the exponents, and so we have 1 plus 1/2, which is 3/2, and then if we multiply this by -3, the 1/3 and that 3 will cancel out, so we just have negative x to the 1/2 power. Okay, and so now we can take the derivative of our function. So if we do that, y prime will be equal to the derivative of 1/3 times x to the 3/2 power. We can just use the power rule for derivatives here. We'll multiply the exponent down and then subtract 1 from the exponent. So we'll have 1/3 times 3/2 times x to the 1/2 power, right? 3/2 minus 1 will be 1/2. And then we'll subtract the derivative of x to the 1/2 power. We'll do the same thing. We'll use the power rule again. We'll have 1/2 times x to the negative 1/2 power, since 1/2 minus 1 is negative 1/2. Okay, and so then to simplify, this 3 and this 3 will cancel out, and so y prime is equal to 1/2 times x to the 1/2 power minus 1/2 times x to the negative 1/2 power. Now we can pull out a common factor of 1/2 from each of these terms, and so then we'll have that this is equal to 1/2 times x to the 1/2 power minus x to the negative 1/2 power. Okay, and I'm going to keep this negative exponent as it is for now. Normally I would move that to the denominator so that we have a positive exponent, but it'll be easier to work with it like this for now, and so this will be our derivative that we will plug into our arc length formula. Now the only other thing that we need to determine is what are our bounds of integration, right? What are the two values of x that we want to calculate the arc length between? Now we're given 2 points in this case, but since we're working in terms of x, we're only interested in the x coordinates of these points. So our bounds of integration will be from 0 to 4. Okay, so we're going to ignore the y coordinates because they don't matter when we're working in terms of x. So this will be equal to the integral from 0 to 4 of the square root of 1 plus our derivative squared. So we'll have 1/2 times x to the 1/2 power minus x to the negative 1/2 power, and then that will be squared, and that will be multiplied by dx. Okay, so now that we have our derivative written in here, I'm going to erase this work so we have more room to work on the next step. And so if we simplify this by squaring each part of this quantity, this will be equal to the integral from 0 to 4 of the square root of 1 plus 1/2 squared, which is going to be 1/4, and then we have this quantity squared as well. So we have x to the 1/2 power minus x to the negative 1/2 power squared times dx. Okay, so we just squared both of these factors here. And so now what we want to do to be able to solve this integral is to expand this squared quantity. Okay, so we're going to multiply this quantity by itself, and so there is a quick trick to that. We will square the first term, and then add the two terms multiplied together, and then multiplied by 2, and then add the last term squared. Okay, so what we'll have is that this is equal to the integral from 0 to 4 of the square root of 1 plus 1/4 times our first term squared. So x to the 1/2 power squared will look like this. We'll have x to the 1/2 power squared. And then we will add these two terms multiplied together and multiplied by 2. So we'll have 2 times x to the 1/2 power times negative x to the negative 1/2 power. And then we will add our last term squared. So we'll have negative x to the negative 1/2 power squared. And that is it for that quantity. And so then we'll multiply by dx. Okay, and so if I clean up my work here, we can simplify further. And so we'll have that this is equal to the integral from 0 to 4 of the square root of 1 plus 1/4 times x to the 1/2 power squared. And so if we multiply those exponents, we'll have 1/2 times 2, which is 1. So we have x to the power of 1, or just x. And then our next term is 2 times x to the 1/2 power times negative x to the negative 1/2 power. So we're at least going to have minus 2. But then x to the 1/2 power times x to the negative 1/2 power, if we add those exponents, is just 0. So we have x to the power of 0, which is just equal to 1. So we have negative 2 times 1. And so we just have negative 2. Then for our last term, we have negative x to the negative 1/2 power squared. Squaring this will get rid of that negative, so we know we're going to be adding the last term. And then negative 1/2 times 2 is just negative 1. So we have x to the negative first power, and then we have dx. All right, and so now that we have simplified that giant quantity, we can now distribute this 1/4 through this quantity. And so we'll have that this is equal to the integral from 0 to 4 times the square root of 1 plus 1/4 times x minus 2 times 1/4, which is 1/2, plus 1/4 times x to the negative first power times dx. All right, and so if I clean up my work again, we can add our like terms, which is just 1 and negative 1/2, so we can combine those to be positive 1/2. And so this will be equal to the integral from 0 to 4 of the square root of 1/4 times x plus 1/2 plus 1/4 times x to the negative first power times dx. Now to simplify further, I notice that each of these terms is divisible by 1/4. And so if I divide each term by 1/4 and pull that out, this will be equal to the integral from 0 to 4 times the square root of 1/4 times x, because if we divide 1/4 out of this term, we just have x, and then 1/2 divided by 1/4 is going to be equal to 2, because 1/4 times 2 is 1/2, so we have plus 2, and then if we divide out this 1/4, we just have plus x to the negative first power, and then multiply by dx. Okay, and so now we can take the square root of each of these factors, since they're being multiplied together, and so the square root of 1/4 is 1/2, and so if I clean up my work again, this will be equal to the integral from 0 to 4 of 1/2 times the square root of x plus 2 plus x to the negative first power times dx. Okay, and then we can pull this 1/2 to the outside of the integral, and so I'm just going to rewrite that. We will have 1/2 times the integral from 0 to 4 of this square root function. Okay, so that was a lot of work, that was a lot of simplifying, but now we have a simplified integral that we are almost ready to integrate. Unfortunately, we have this composite function where if we set u equal to the inside function, the derivative of u is nowhere within our integral, and so we can't use u substitution. Once again, just like in our previous example, we need to manipulate what we have here so that we do have an integrand that we know how to integrate. And so it can be difficult to determine how to manipulate this function, but something that you always want to try is to factor something out. And so what I'm going to try to do is factor out x to the negative first power. And here's why I'm going to do that. Note that we can rewrite these terms in the following way. This will be equal to 1/2 times the integral from 0 to 4 of the square root of x squared times x to the negative first power plus 2 times x to the negative first power plus x to the negative first power. Now what I did here was I just rewrote these two terms to be expressed with an x to the negative first power, right? So x squared times x to the negative first power, if we add those exponents, is just x to the first power, which is what we have right here. And 2 times x to the first power times x to the negative first power is still equal to 2, because if we add these exponents, 1 plus negative 1 is 0, and x to the power of 0 is just equal to 1, and so you'd have 1 times 2, which is equal to 2. All right, and then I didn't rewrite this term, it's still x to the negative first power. And so now what we can do, because I've rewritten these two terms, is pull out a common factor of x to the negative first power, and that's going to leave us with a quadratic equation that we can factor. Okay, so if I clean up my work again, this will be equal to 1/2 times the integral from 0 to 4 times the square root of x to the negative first power times x squared plus 2x plus 1, and then we can multiply by dx right there. Okay, so I just pulled x to the negative first power out of each of these terms, so we're just left with x squared, we're left with 2x, and we're left with 1 if we divide x to the negative first power by itself. And so that's where this 1 comes from. But now we have a quadratic that we can factor. And since the coefficient of the x squared term is 1, we just have to ask ourselves what factors of the last term, 1, added together will equal the coefficient of the middle term. And so that's just 1 and 1. And so this factors to become x plus 1 times x plus 1, which is equal to x plus 1 squared. And so if we rewrite our integral by using that factorization, this is equal to 1/2 times the integral from 0 to 4 times the square root of x to the negative first power times x plus 1 squared. And that's still multiplied by dx. And now what we can do is take the square root of each of these factors and simplify our integral even further. And so if I clean up my work again, we can now rewrite our integral and have that this is equal to 1/2 times the integral from 0 to 4 of the square root of x to the negative first power. And so we'd have x to the negative first power to the 1/2 power, right? That's the same as the square root. And 1/2 times negative 1 is negative 1/2. And so we'll have x to the negative 1/2 power times the square root of x plus 1 squared. And so the square and the square root will cancel out, so we'll just have x plus 1. So that's multiplied by x plus 1 times dx. Okay, so we're almost done simplifying. We have finally eliminated that square root, so now we have an integral that's going to be a lot easier to integrate. And now the only thing we have left to do to simplify is to distribute this through this quantity. So we'll multiply x to the negative 1/2 power to each of these terms. So if we do that, this is equal to 1/2 times the integral from 0 to 4 of x to the negative 1/2 power times x, which has an exponent of 1. So 1 plus negative 1/2 is positive 1/2. So we have x to the positive 1/2 power plus x to the negative 1/2 power times 1, which is just x to the negative 1/2 power, and that will be multiplied by dx. Okay, so now we are finally ready to integrate our terms with respect to x and then solve this definite integral. And that will give us the arc length of our curve from 0 to 4. All right, so I'll clean up my work again, and we can integrate each of these terms using the power rule of integration. So we'll add 1 to the exponents and then divide by that new exponent. And so this will be equal to 1/2 times x to the 3/2 power divided by 3/2 plus x to the 1/2 power divided by 1/2. And that is evaluated from 0 to 4. Okay, so 1/2 plus 1 is 3/2, so we divide by 3/2. And then negative 1/2 plus 1 is positive 1/2, and so we divide by positive 1/2. And so now remember, dividing by a fraction is the same as multiplying by the reciprocal of that fraction. And so the reciprocal of 3/2 is 2/3, and the reciprocal of 1/2 is 2. And so this is equal to 1/2 times 2/3 times x to the 3/2 power plus 2 times x to the 1/2 power, evaluated from 0 to 4. And so I'll clean up my work one more time here. And now we can evaluate this expression at 4 and subtract the evaluation at 0. And so if we plug 4 into this expression, we will have that this is equal to 1/2 times 2/3 times 4 to the 3/2 power plus 2 times 4 to the 1/2 power. And then we will subtract plugging 0 in. But 0 plugged in for x is just going to produce 0 because 0 to the 3/2 power is 0. Times 2/3 is still 0, plus 2 times the square root of 0, or 0 to the 1/2 power. That's just 0, and so both of these terms are 0, and so we're just subtracting 0. Okay, and so to simplify further, this is equal to 1/2 times 2/3 times 4 to the 1/2 power cubed, right? That would be the same as 4 to the 3/2 power. We take the square root of 4 and then cube it, and so the square root of 4 is 2. And so we'll have 2 cubed right here. And 2 cubed is just equal to 8. So I'll rewrite that to be 8. So we have 2/3 times 8 plus 2 times 4 to the 1/2 power, which is just the square root of 4. So we have 2 times 2. So that's going to be equal to 1/2 times 16/3 plus 4. And 4 is the same as 12/3. And so 12/3 plus 16/3 will give us 28/3, and so this is equal to 1/2 times 28/3, and 28 divided by 2 is 14, and so this simplifies to 14 divided by 3, or 14/3, and that is the arc length of this function from 0 to 4. There was a lot of work to get there, but in the end we were able to solve for that arc length. It just took a lot of manipulation of our integral. All right, so now you've seen that the arc length problems can get pretty complex. Your integral can be pretty hard to solve sometimes, but as long as you look for ways to manipulate that so that it's easier to solve, whether that be by factoring or using u substitution, you should be all right in the end. You just have to think of creative ways to make your integral easier to solve. And knowing how to do that will come with time as you practice more of these problems. Okay, but with that, this is the last example for this video, and so if you have any questions, feel free to leave those in the comments, but if you don't have any questions, this is all I had for now, so I will see you next time.